created by MindSticks Foundation Trust. Hello, students, and welcome to today's Explainer. I'm so glad you could join me. Let's quickly look at our plan for today. First, understanding circle segments. Next, deriving the area formula. Then, solving example problems. And finally, time to practice. So keep your notebooks handy and let's get right into it. Section 1. Understanding circle segments. Identifying minor, major, and semicircular segments. Before we even think about crunching numbers, we have to know exactly what geometric shapes we're dealing with. So let's start at the very beginning. What exactly is a segment of a circle? Well, simply put, it's the region bounded by a chord and its corresponding arc of the circle. Just think of a chord as a straight boundary line, right? It cuts straight across the circle from one edge to another. And this straight line, along with the curved edge of the circle, the arc, traps a specific little area inside. That enclosed space, that's what we call our segment. Now, if you look closely at the diagram on your screen, notice how that straight chord, AB, clearly slices the circle into two unequal parts. The smaller area, tucked between the chord and that minor arc, AXB, is called the minor segment. And naturally, the leftover, much larger area bounded by the major arc, AYB, is our major segment. Oh, and by the way, if that chord happens to pass right through the exact center, it becomes a diameter, cutting the circle into two perfectly equal semicircular segments. But for today's calculations, our main star is going to be that minor segment. Moving right along to Section 2. Deriving the area formula from sector to segment. All right, let's dive into the derivation. I want you to follow this logical sequence closely with me. Because honestly, understanding the why is so much more powerful than just memorizing the what. I'd like you to carefully observe the figure shown here. See that center point O? From O, we've drawn two straight radii, OP and OQ, going right down to the edges of our chord PQ. By doing this, we've essentially sliced out a large piece of the circle, almost like a slice of pizza. We call this whole slice a sector, named OPXQ. But look closely inside this large sector. Sitting right there on top of our segment is a triangle OPQ. Do you spot it? Our segment PXQ is just resting right below the base of that triangle. And this brings us to a really beautiful piece of geometric logic. How do we isolate just that little segment at the very bottom? Well, step 1, we look at the entire slice, the total area of the sector OPXQ. Step 2, we figure out the area of that triangle OPQ sitting at the top part of the slice. And step 3, this is the master stroke, we simply subtract the triangle's area from the total sector's area. Think about it. If you have the whole sector and you just take away the triangle, what's left behind? Exactly, only the area of our segment. It's brilliant. So by putting together the mathematical formulas for the area of a sector and the area of a triangle using the sine of the central angle, we arrive at this final, very elegant equation. Please go ahead and write this down carefully in your notebooks. The area of a segment is equal to r squared multiplied by the entire bracketed quantity pi times theta divided by 360 minus sine theta divided by 2. Let me say that one more time, nice and slow for you. R squared times the quantity pi times theta divided by 360 minus sine theta divided by 2. And just a quick note, based on the trigonometry we've covered so far, we'll use this specific formula whenever our central angle, theta, is 90 degrees or less. Section 3. Solving example problems, applying the formula step by step. Okay, now that we have our mathematical tool, let's shift from theory into practice. Don't worry at all. We are going to walk through some textbook examples step by step together. Let's read through example 1. In a circle, if the central angle AOB is given as exactly 30 degrees and the radius OA is given as 12 centimeters, what is the area of the segment? They've also kindly instructed us to use the specific value of pi as 3.14. Now, before we start scribbling any numbers down, it's always best to visualize the problem first. Look at the visual on your screen. We have our radius r equal to 12. We have our central angle theta equal to 30 degrees, and we're looking for the area of that small shaded region down at the bottom, the minor segment AXB. Doing this mental mapping ensures we know exactly which pieces of our formula match up with the physical parts of the circle. So let's patiently walk through the calculation. Step 1, we substitute our given values right into the formula we just noted down. R becomes 12, so we have 12 squared resting outside the bracket. Inside the bracket, we have 3.14 times 30 divided by 360, minus sine 30 divided by 2. Step 2, we simplify. 12 squared is 144. Now, 30 over 360 simplifies nicely to 1 over 12. And from our trigonometry tables, we know sine 30 is exactly 1/2. So that second part becomes 1 over 2 multiplied by 2, giving us 1 by 4. Step 3, when you calculate the fractions inside the bracket and then multiply by the 144 outside, we land perfectly on our final area, exactly 1.68 square centimeters. And, this perfectly illustrates just how adaptable our logic really is. Look at example 2 here. In this case, the chord AB subtends a right angle, a full 90 degrees at the center P. The radius is 10 centimeters. Now, even though the angle is much wider, the fundamental logic remains absolutely identical. You find the area of the massive sector PXB. You find the area of that right-angled triangle PAB, and you simply subtract the triangle from the sector. Following those exact same steps gives us a minor segment area of 28.5 square centimeters. The formula works flawlessly every single time. Let's kick it up a notch and see how this builds into more complex exam-style questions. Take a look at this next figure. Here we have a regular hexagon inscribed perfectly inside a circle with a radius of 14 centimeters. The question asks for the area of the region between the circle and the hexagon, meaning those 6 shaded minor segments around the edge. Believe it or not, it's just another subtraction problem. You calculate the area of the total circle, then calculate the area of the entire regular hexagon, and simply subtract the hexagon from the circle. That's the secret to geometry. It's really just a beautiful puzzle of adding and subtracting shapes. Section 4, time to practice, testing your knowledge. All right, we've covered the derivation and we've gone through the guided examples together. Now it's time for you to test your independent understanding. Before we jump into the practice problem, let's summarize the absolutely crucial points you need for your exams. First, always correctly identify your segments by locating the chord and the corresponding arc. Second, firmly grasp the underlying logic. The area of the segment is simply the area of the total sector minus the area of the inner triangle. And third, absolutely memorize your working formula. R squared times the quantity pi theta by 360 minus sine theta by 2. If you can remember these 3 things, you are going to be exceptionally well prepared. I'm pointing your attention now to practice set 7.4 in your materials, specifically question 1. You'll see the figure on your screen. The center of the circle is A. The central angle BAC is given as 45 degrees, and the radius AC is given as 7√2 centimeters. Our goal is to find the area of the shaded segment BXC down at the bottom. So here is my challenge to you, students. Look carefully at this problem. You have your radius, you have your angle, and you have your formula. Can you apply today's lesson to find the exact area of segment BXC completely on your own? I highly encourage you to take out your pen and paper right now and solve this before your next class. You've got all the tools you need to succeed. Thank you so much for learning with me today, and keep practicing your mathematics.